Welcome to this lesson on data handling, and in particular we're going to focus on how to calculate relative frequency in this video and how we interpret the outcomes. So as a starter then, okay, wanted to have a go at this. So a fair dice is rolled 60 times. How many times do we expect the dice to land on the number 5, a number less than 3, or a number that is a factor of 30? I'd like you to pause the video. When you've had a go at the questions, press play to go through the solutions. So press pause now, please. Okay, welcome back then. All right, and so what do we know then? Well, we know this dice has been rolled on 60 occasions, okay, and it's a fair dice. So on a dice, we've got the numbers 1, 2, 3, 4, 5, and 6. So there's 6 numbers on this dice, okay, one of each number. So how many times do we expect the dice to land on number 5? Well, first of all, we've only got one number 5. So the probability of it landing on a 5 is 1 out of 6. Okay. Now that's for each individual go. So if we're rolling this dice 60 times, then we need to multiply this by 60, or we're effectively finding 1/6 of the 60 goes. Okay, so in this case, then we just divide 60 by 6 and multiply the answer by 1. So 60 divided by 6 is 10. 10 times 1 is 10. So we would expect the dice to land on the number 5 on 10 occasions. What about a number less than 3 then? So how many of the 60 rolls of the dice would we expect to land on a number less than 3? Well, in this case, less than 3, the dice could land on a 1 or a 2. So the probability of it landing on a number less than 3 is 2 out of 6. And again, because we've done the experiment 60 times, we are going to find 2/6 of 60. So we're going to do 60 divided by 6 and then multiply the answer by 2. So 60 divided by 6 is 10. Okay, so that's 10. 10 times 2 is 20. So we would expect it to land on a number less than 3 on 20 occasions. And what about a number that's a factor of 30 then? So first of all, we need to remind ourselves what a factor of a number is. Well, a factor is a number that goes into 30, for example, but without a remainder. So what's the factors of 30? So the factors of 30 are 1, because 1 goes into every whole number. 2 goes into 30 exactly. 3 goes into 30 exactly. 4 does not go into 30, 5 goes into 30, and 6 goes into 30. Okay, so they're all the factors on the dice of 30. So that's 5 of them. So 5 of the 6 numbers are factors of 30. So the probability of a dice landing on that is 5 out of 6. And we need to times that by 60. So we need to work that out. So again, divide by the bottom number. So 60 divided by 6 gives me 10. And times it by 5. 10 times 5 is 50. So 50 times we would expect out of 60 the dice to land on a factor of 30. Okay, so we're going to be talking about relative frequency. So we need some information, or we need an experiment to be conducted in order for us to see what the information we're dealing with is. So in this example, we've got a biased spinner and it's numbered 1 to 3. And it's spun 100 times. The results are seen in this table here. So it's telling us here that the spinner landed on number 1 11 times, it landed on the number 2 34 times, and it landed on the number 3 55 times. Okay, so the spinner is spun one more time. Use this table to work out an estimate for the probability that a 3 will be spun. So what's the probability that when we spin it again, this spinner will land on a 3? Well, we've got to use the information that we've been provided. For a start up here, we know that there are the experiment was done 100 times. So the probability will be out of 100. And then we need to know how many times out of the 100 it landed on the 3. Well, in this case, it was 55 times. So it would be 55 times out of 100. Now that's our probability based on the experiment and the information we got from the experiment for the spinner to land on a 3. So there's my estimate for the probability that a 3 will be spun on the next go. So just a bit of information for you then. So to work out what's called relative frequency, okay, we work out the number of times from the experiment that an event happens. We put that in a fraction over the total number of trials. So relative frequency can also be known as experimental probability, because the information that we're getting is as a result of an experiment. So from the previous example, we had 55 times the spinner landed on a 3 out of 100. So it's all this probability here came from the experiment, and the frequencies were relative to the outcomes that were recorded. Okay. So quite often, one of the things that is asked when we're dealing with an experiment is how many times do we need to do the experiment before we're happy with the outcomes? Well, the true answer to that is there isn't a fixed number of trials, but what we say is that the more trials we do in an experiment, the better and the more reliable our results are likely to be. So as a general rule, I would say that an event that occurs at least 100 times would provide enough evidence to see whether the outcomes are fair or whether they're biased in any way. Anything less than that, really, we need to be doing the experiment more often. So, example 2 then. This is a survey which noted the colour of the cars that entered Asda's car park. So, there were 16 red cars, 7 blue, 11 white, and 16 black. Okay, so that's what was recorded in this experiment. Based on that information, what's the experimental probability or relative frequency that next car coming into the car park would be a red car? So we know from here that there are 16 red cars. Altogether in this car park, we need to work out the total number of cars that entered, because we need to know what it's out of, how many trials, how many cars, colours were noted. So I would need to add together all of these frequencies in here. So altogether, I've got 50. Okay, so I now know that if I'm going to use this information, my experimental probability or relative frequency is going to be out of 50. So I can tell from the table that there were 16 cars recorded as red. So the experimental probability is 16 out of 50. Sometimes I'm asked to put that into a decimal. And if I was going to do that, then I convert that into a decimal, either on the calculator or by using my other skills of scaling up or down of powers of 10. So out of 100, that would be 32 out of 100. So 0.32. What about the probability that the next car coming in would be a blue? Well, again, it's going to be out of 50. And blue cars, there were 7, so 7 out of 50, or as a decimal, 0.14. A white car, we can see, is 11 out of 50 from the table. So in this case, 0.22 as a decimal. And what about a blue or a black? Well, if we want to know about a blue or a black, then we need to combine the two outcomes together. And OR in probability means to add. So there are 7 blue and there are 16 black. So I would need to add those two together first. So adding them together gives me 23. And that would be 23 out of 50 based on this data here. So if I wanted to put that into a decimal, that is equal to 0.46. Okay, here is your main task. There are 3 questions. I want you to use the information from the questions, and I want you to have a go at the answers. You need to pause the video now to have a go, and then press play when you're ready to go over the questions. Press pause now. Okay, welcome back then. So question 1 then, we could see in the question here that this spinner was spun 500 times. It's got 1 to 5 on them. Here's the number of times it landed on each number. So here's the frequencies. So what's the relative frequency of scoring a 2? So for A part 1 then, scoring a 2, there, it landed on a 203 times. And we know that's out of 500. Put it into a decimal, it's 0.206. So any of those 2 answers there would be acceptable. Number 2, on a 4. So here's your 4 here. There's 96. So 96 out of 500, or as a decimal, 0.192. And part B asks us, do the results suggest that Solomon's spinner is fair? Well, if they were fair results, then the probability of it landing on a 1, 2, 3, 4, 5 is 1 out of 5. So if we find a fifth of 500, because there was 500 trials, so we divide 500 by 5, which gives me 100, we would expect each of the numbers to land on 100 times each. But in an experiment, we get lots of different outcomes. But if I have a look at all these outcomes in the table, they're all very close to 100. So that would suggest to me that the results are fair on this spinner. Number 2 then, we've got 87 times a pin lands point up. So the probability estimated for point up is 87 out of 210, which is 0.414 to 3 decimal places. Part B, point down, well, we'd have to find out how many times it landed point down, so find the difference. So it's 123. So that'd be 123 out of 210. So as a decimal, that's 0.586, correct the 3 decimal places. Okay, sorry, we're being asked for 2 decimal places, so I need to correct these. So 0.41 to 2dp. And on this one, we've cut it off here, so 0.59 to 2dp. Okay, just making sure we got the question read correctly there. And the third and final question, then 400 people were surveyed about their favorite flavor of crisps. Explain why it's reasonable to use these figures to estimate the probability. Well, it's reasonable because at least there is enough trials in this case, over 100, over 100. That's the key figure, isn't it? Anything over 100. Part B then, what's the probability of the next person choosing salt and vinegar? Well, salt and vinegar got 75, so 75 out of 400. As a fraction in its simplest form, it will cancel down to 3/8. And part B, for ready salted, that would be 150 out of 400, which is 3/8. Apologies, that's that one. And this one would be 3 out of 16 cancelled down here. Okay. Right, the check-in question then. Pause the video and have a go to see. You need time to read it to see if you can fill in the rest of this table here. So pause the video now and have a go, and then press play. Okay, welcome back then. So this is an example of how a question may be set out in an exam. Okay, so we've got here the coin being thrown. Okay, and they're doing it in recording the results in groups of 10. So the first 10 throws, there was 2 heads. So in here, that's 2 out of 10, which as a decimal is 0.2. After the next 10 throws, there was another 4. So altogether, that's 6. So that's 6 out of 20. 6 out of 20 is 0.3. So to fill this one in here, we need to add the next bit of information on that. That's 3 more heads. So that's now 9 heads out of 30. And as a decimal, that's 0.3. And after the last 10 are thrown, we add another one on. So that's 10 out of 40, which is 0.25. So well done if you filled that table in correct. Now, using the above results, write down the best estimate for the probability of getting ahead when this biased coin is thrown. Give a reason for your answer. Now, the best answer is always the answer given for the most number of trials. So in this case, that's after 40 trials. So the best estimate is 0.25, and it's after the most trials. Okay. I hope this lesson has helped you. Okay, so thank you very much for listening and stay safe.